All right, so we left off talking about how hydrogen is not a renewable resource. And the reason why we're talking about why hydrogen is not a renewable resource is because I think fuel cells are important, right? And so I was talking about hydrogen fuel cells and how they won't be a source of energy for the solution to energy problems in terms of hydrogen being the source of fuel. Now, there might be a possibility that in some way they become a mechanism for transporting energy from location to location and then burning it cleanly, because when they do burn, their product is only water, which is a very clean condition, right? So that's the deal with hydrogen fuel cells. Now, also, we talked about how if I have hydrogen gas combining with oxygen gas to release water, right? This process, we know the delta G for this process. Now we know what delta G is. We're not surprised by what that means anymore. We want to know if this reaction is spontaneous. And I showed you the video of the Hindenburg blowing up. So that's a way that you can remember a blimp full of hydrogen, or maybe you've seen a hydrogen balloon explode, or it's all over the internet, that sort of thing. Hydrogen gas is explosive, flammable, combines with oxygen. This, therefore, is a negative delta G. And so the opposite reaction, taking water and getting back the hydrogen, is going to have the same value here of delta G, but it's just going to be a positive, right? Not spontaneous, going to require energy. Okay, so, and we talked about this one and that one already, and we started doing these cell notations. Okay, now, we talked about how this cell notation here mimics kind of a picture of a fuel cell where you have an anode, some sort of electrode, cathodic portion, right? These are solutions or containers full of solution, or electrolyte is what they call it. It doesn't always need to be liquid, right? It can be just hydrated conditions. All right, so then you have a salt bridge that goes in between here somehow, and you have your ions in here. And so this cell notation mimics that, in that we have our electrode surface where the oxidation is occurring. I know this is the oxidation because this is the anode side. And then we have our anode electrolyte, and then we have our salt bridge, and then we have our cathode far right, the place where reduction is occurring, the thing that's being reduced, and then the cathodic solution there. Okay? So, we're not going to spend a lot of time doing this because the kinds of times they give you problems on that, it's such a fringe kind of thing to be aware of that it'll be kind of a more easy problem. All right? All right. So, in the past, and just this last class, we reminded ourselves, and we've talked about how simple single replacement reactions like this one, where I have zinc metal combining with copper ion, and the zinc, because it's more reactive, gives up its electrons to form an ion and results in the copper ion becoming metallic. Right? We can put zeros on those metals to remind ourselves that they're metallic. Okay? And we said that this reaction has a negative delta G, or in other words, this reaction occurs spontaneous, occurs as it's written left to right. But the reverse reaction, zinc ion, right, combining with copper metal, where we're expecting the zinc to take the electrons from copper and make copper ions, that process has a positive delta G. It's the exact opposite, right? So it's the same value again, just a different sign. And so that reaction is not spontaneous and will not occur going that direction by itself. So, we could predict this before by looking up a table of activity table showing us which compounds were more reactive. And I don't know if you remember this. Let me bring this table up really quick. Okay, so here we have the activity table. Whoops, let's go back to it here. Here's this activity table. Remember this activity table? It has different elements, and it lists them, and it has two lists here, one where it's just the element and the other where the element is in its ionic form, right? And we see the less reactive elements up at the top, the less reactive elements at the top here with gold, mercury, silver, and copper. We see the more reactive cesium, potassium, rubidium down here at the bottom. All right. So what we're showing is that, and we can look at our example over here. Zinc is more reactive than copper because zinc is lower down on the reactivity totem pole, so to speak, right? You see zinc down here near the middle, and copper is up here at the top. So copper prefers to be elemental, solid, right, metallic, while zinc prefers to be in the ionic form relative to where copper is. Okay, so remember this reactivity table. If not, this is the first time you've seen it, but that's okay. And we're going to talk more about this type of thing. However, this time around, when we talk about reactivities, we're going to provide actual quantitative values to relate to the activity, the level of activity. Okay? If gold, for example, is going to take or give up 3 electrons, that's an oxidation. Or if gold ion here is going to take 3 electrons, that's a reduction. So going from left here, gold to right, is an oxidation. And going from right to left, that's a reduction, right? And so when there's a general relative activity table provided, you can identify which one of these reactions would be spontaneous, right? By looking at which ones want to be more reactive, which ones are more reactive, and therefore the more reactive ones want to give up electrons, right? And the more reactive ones are listed down on the bottom. Another way to think about it is the more reactive ones want to be ions, right? And the less reactive ones want to be metallic. All right, so that's our reactivity table there. Let me see, here we go. So we're going to now delve into the idea that these values can be quantitative. We can quantitate them. We can quantitate how much reactivity or the level of reactivity that they have. And this quantitation is related simply to other atoms, right? When they do this, they identify the hydrogen's reduction would mean hydrogen ion being reduced by an electron to form hydrogen gas. So we need 2 hydrogens and 2 electrons. This reduction here would be identified as, we would just give it a value. In this case, we're going to call it 0 volts. All right, so volts are the units that we utilize, and a volt is 1 joule for every coulomb. Now, a coulomb is a measurement of the number of electrons that transfer in a given chemical reaction. And it's kind of just a set number. It's 96,500 about, and it's just a number of electrons. We don't have to worry too much about that at this point. This will be your first introduction to it, and then we'll deal with it later. But we call this reduction potential, or the value in volts, how much activity this specific process, and then they're always provided as reductions. We call this E, which is a shame because it's related to, it seems like it's just like energy. We called E energy before. But it's okay that it's E, and that kind of reminds us of energy because it is directly related to energy as well. It's related to delta G, it's related to energy, and so it's not a bad thing that is E. We call E the potential at which this process or any process wants to occur. And again, in the table, they're always provided as reduction potentials, or in other words, things receiving electrons. Okay? So, if I have a high value, like if I have this reaction here that says 0 volts, all right, But then here's another reaction where I have some element and I'm giving, or some ion, and I'm giving it an electron, and it forms this. And let's say this is a negative 1.0 volts. All right. Okay, get this out of here. All right, there we go. So I have another reaction here that I'm comparing the voltage to this one. This negative one, right? Just like the delta G and the delta H, the negative sign indicates that the process wants to occur. So going from left to right, this is a release in energy. Okay? So when I look at this process, I can say that this bottom one here has a more negative delta G going to the right, whereas the top one has less negative, maybe even a positive delta G going to the right. Okay? And these are related to each other. And we'll show you in a minute how E, or the potential, can be related to delta G. All right, so here is a list of cell potentials. And this is a typical kind of list that they'll provide for you when they're asking you questions about this, or that you'll utilize to answer these types of questions. And again, you can read the top. It says these are standard reduction potentials. So these are potentials of things being reduced. And so everything on there is the reduction of something. And again, these aren't full reactions. These are what we call half reactions. So in this, if it's just a reduction potential, you notice that it's not a redox potential, it's a reduction potential. There's no oxidation coupled with this, but what we're going to do is we're going to take other reactions and couple them with these, and that will give us the resulting potential for that chemical reaction, and it'll also give us the voltage that you could create if you were to make a battery or a cell from those two reactions. All right. So we can identify the potential for a given cell by looking at one of these half reactions as a cathodic reaction and one of these half reactions as an anodic reaction. Now all of these are reductions. So these reactions here are how the reactions would occur at a cathode, because again, cathodes are where the reduction occurs. On the other hand, this here, I mean, if you're going to identify the voltage, if you want to identify the voltage for a given chemical reaction, let's say I had this process occurring where I have hydrogen ions, right? And they're going to be combining with something. They're going to be taking electrons in my process here. They're going to be combining with something that will give them electrons. I'm not going to be able to choose this thing because this thing doesn't want to give electrons. It wants to take electrons. So I'm going to combine it with this species over here. And then I'm going to draw the products where this goes to the X plus and the hydrogen, H plus, goes to the hydrogen gas. So I have a couple of redox potentials, reduction potentials provided for me, half reactions. I combine them together in a chemical reaction. This one here, H plus going to H2, occurs just like this is written. So that contributes 0 volts to this process. This one over here, on the other hand, I have reversed it, right? So X has gone to X plus and has released an electron to the hydrogen here. All right. So that means that to this final reaction, the potential for this final reaction here, I contribute this 0 volts because this is the reaction that contributes. But because I have a reverse reaction occurring here, I contribute the positive 1 volt. So the result is the 0 plus the positive 1.0 volts. And I have 1 volt being my total reaction process that will be, I mean, that's the total potential associated with that overall reaction. Okay, so we'll go over some problems like that and see how this works. So now let me go back to this slide. Some people like to, and this is kind of the typical thing, and you're welcome to do it, but it's in my mind silly to try to memorize little phrases like this that are not going to stick very long. Some people say the E cell is cathode minus anode, right? Cathode minus anode. Well, you can do that where you take the E naught of the cathode here and then change the sign for the E naught on the anode here. But people forget and they go, oh, is it anode minus cathode, cathode minus anode? Try to invent some way to remember. That's all a waste of time. You don't need to worry about that. All you have to do is look at the chemical reaction that's proceeding and see how you can tell that this reaction up here is occurring just like it's written here, right? Hydrogen ion to hydrogen gas. So that's 0 volts. This one here is not occurring just like it. It's the reverse. So it's the positive 1 volts. So then I know it's 1 and 0, and I just combine them together. And so the resulting voltage will be the reaction voltage for that process. So here's an example. We have a chemical reaction. We have a couple of redox potentials here that we're going to be able to select from, and we want to know the potential, the voltage associated with this overall reaction. So I have nickel solid going to nickel ion. I see that. That is this reaction here, except for it's reversed, right? Because here I have nickel ion going to nickel solid. If I take nickel ion and go to nickel solid, then this is supposed to be a negative 0.25. So that means up here I'm going to contribute a positive 0.25, right? Because this is nickel ions going to nickel solid, meaning it releases or is a negative 0.25 volts. But this one here is nickel solid going to nickel ion. So that's a positive 0.25 that I'm contributing to this reaction. On the bottom one here, I have hydrogen peroxide going to water, right? Here's my hydrogen peroxide, here's my water, there's even the hydrogen ions included there. So this one is occurring in this chemical reaction above, just like it's written. So I take that value, 1.77, I add it to the opposite of this, not negative 0.25, but positive 0.25, and my result is going to be my voltage for this chemical reaction. All right? So if I made a battery then where nickel was, is nickel going to be the anode or the cathode here? Talk with your neighbor. Identify whether nickel is going to be the anode or the cathode. Remember what we talked about in terms of how you can, what an anode is, what's occurring at the anode, what's occurring at the cathode, all right? And talk to your neighbor. Take a few moments and see if you can find out what is nickel. Is nickel the anode or the cathode? Okay. In this process here, we see that nickel is going from a solid to a 2+ ion, right? Metallic to an ionic state. And the charge, or the oxidation number here is 0. The oxidation number on this atom is +2. 0 to +2, that's not reducing it. That's oxidation then. So nickel is being oxidized. That means the nickel metal is the anode. Oxidation occurs at the anode. And we remember that because oxidation is starts with a vowel and anode starts with a vowel. Okay, so that's our anode. And the anodic reaction is nickel going to nickel ion. The cathodic reaction is hydrogen peroxide being reduced to water, right? Now I didn't look at the oxidation numbers, but I didn't need to. And if I were to look at it, I would find out that yes, for sure there's a reduction occurring. I didn't need to look because I knew that nickel was the oxidation. All right, so here's another. We talked about methods for remembering. I don't know if we actually talked about it in this class, but in 105 we did, and I think that you guys have heard about this before, but we'll review it now also. Find some paper here. We have a couple ways to remember. Oxidation is loss. Oil rig. Reduction is gain. Oil rig. Right? Those are little mnemonic devices to help you remember that oxidation is loss of electrons. Reduction is gain of electrons. All right? Spontaneous reactions are ones that have a positive delta E. All right? So when the overall reaction has a positive delta E, that means that reaction is spontaneous. And we'll look at this to remember as well. Okay, so what's the voltage for, or E naught, right? What's the potential for this reaction, and is it spontaneous? Is it spontaneous? All right, so we have a list of reduction potentials down at the bottom there. I'll let you and your neighbor try to figure this out, try to find out what the reduction potential is here, and if it's spontaneous. All right, ready, go. All right, so looking at these reduction potentials down here, we see that if copper ion is converted to copper metal, then that gives us a positive 0.3 volts. And up here we have copper, but we don't have copper ion going to copper metal. We have copper metal going to copper ion. So the copper's process, which is what, reduction or oxidation? It's oxidation. Copper solid going to copper ions is oxidation. So this oxidation is contributing not a 0.34, but a negative 0.34 to this process. So the copper going from copper solid to, copper ion contributes a negative 0.34 volts. Okay? And the other process, silver ion going to silver metal, that is a reduction. And so that's this one down here. That contributes what the value is listed there as, a positive 0.8. So if I combine these two numbers together, negative 0.46, no, sorry, positive 0.46. Positive value means that this is a spontaneous reaction, all right? And the voltage that you'll get if you combine these cells is 0.46. Okay? Now, I don't know if any of you noticed or remember about how to balance redox reactions, but this reaction that's provided here, the copper combining with the silver ions to form copper ions and silver metal, is not balanced. And you can tell it's not balanced because you have copper, 0, going to copper with a +2 charge. So each copper is losing 2 electrons, but each silver is only taking 1 electron. Right? So to balance this, you need to put a 2 here. Okay? Now, because these E values that are provided are E naughts, which means standard conditions, which mean 1 molar of the different things that would be in our quotient if we were to draw the quotient for this. So if we were to draw the quotient for this, this is aqueous, this is aqueous. The quotient would be copper ions over concentration of silver ions squared, right? Those are the things that would be in the quotient. Their concentration would be 1 molar, and the resulting E naught that you would get, you wouldn't have to multiply this voltage due to the, let's see, yeah, this is the one that's due to the silver, right? You wouldn't have to multiply that voltage that's due to the silver times 2, because this is, again, an E naught. And E naught means it's not dependent on the coefficient there, it's just dependent on the concentration, and E naughts are standard conditions, meaning 1 molar of all the things that would be in our quotient. All right, so let's take the next one here. Talk to your neighbors. Try to identify whether or not this reaction, whether or not you think this reaction would be a spontaneous reaction, and find out what the E naught for the cell would be. Go. All right, did you get it? Lead contributes a what? A negative 0.13 or a positive 0.13? It's a positive 0.13, right? Because I can see that the reduction potential is a negative 0.13, but here it's not being reduced, it's being oxidized. So it's a positive 0.13. While the copper contributes a negative 0.34 or a positive 0.34. It's a positive 0.34. So positive 0.34, positive 0.13, total is going to be about 0.47, right? All right, and positive value, spontaneous reaction. All right, one last reaction here. Go ahead and find the E naught for this one. It's good practice. Go. All right, so I see that this dichromate ion here going to chromium ion is going to contribute 1.33, a positive or a negative? It's going to be positive because it's just like the way it's listed here, right? This one is being reduced to the chromium ion, and that's just like this is written. The other one, this is opposite. Here we have manganese oxide going to permanganate ion, and this is the reduction of the permanganate ion to manganese oxide. Therefore, we have to make this a negative. So it's a positive 1.33 and a negative 1.695. It's going to leave us with a negative value, showing that this reaction is not spontaneous. Okay, I think you guys got it, right? So, here's our relationship between E, right, and delta G. Delta G can be retrieved from E, or if we have delta G, we can identify E. If we know how many electrons are transferred, and we use a constant to relate the units appropriately. Now, the number of electrons that are transferred is identified by looking at the balanced cell and finding out how many electrons are transferred from one species to another. Okay? And F is 96,500. That's how many coulombs there are for every mole of electrons. All right? So 96,500 coulombs for every mole of electrons. That's the F value. 96,000 coulombs per mole of electrons. N is in moles of electrons. Cell is in joules per coulomb. And coulombs get canceled out here, moles get canceled out here, and our delta G is left in joules. Okay? So, you'll have to pay attention to the joules and not think you're into kilojoules already, right? You'll have to be able to identify that you need that F, and that's going to be fairly easy because there's not other variables that start with F. Faraday's constant is the only one. This equation here will be provided for you. And again, this equation allows you to go from delta G to the E cell. Notice there's a negative sign there, right? Now, this was just an electrochemical decision a long time ago to have E cell be positive, right? It developed in different kind of areas in the chemical world. So delta G always is negative if it's spontaneous, and E cell is positive if it's spontaneous. So we have a negative sign in there. All right, so if we want to calculate the delta G in kilojoules per mole, so we have to make sure we recognize that. And this is going to be probably provided in joules per mole, so in the end we're going to have to calculate it. Of this chemical reaction here, well, we got the voltage before by... oh, no, sorry, we don't need the... Wait. Yeah. Wait, where are we at? Where are we at? Oh, we got the voltage before, 0.46, back on this slide here, right? So we have 0.46, 0.47, and negative 0.365. We can remember those. So we got the voltage there, 0.46, and that goes in here. Again, it's joules per coulomb. That's the units for volts. All right? So the E cell times the Faraday's constant, 96,500. Now, where did we get the 2? We need to get this 2, right? Here it is right here. We need to get this by looking at the chemical reaction and seeing how many electrons are transferred. All right? And so to do that, we need to be able to remember how to balance these reactions. If it's a simple reaction like this, where you can see that the silver ion goes to silver metal and the copper metal goes to copper ions, right? If it's a simple one like that, then we can just look and see 2 electrons are released here, 1 electron is required here, and then we just, like we did before, put a 2 in front of both of those. And now when this process occurs, the change in the number of moles of electrons, or the moles of electrons, we should just say, equals 2. Because this copper needs to take 2, or release 2, for it to be oxidized, and therefore we're going to need 2 silver ions to take both of those electrons. All right, 96,500 times 2 times 0.46 should be a value about 88,800. Is that right? And then we divide it by 1,000. Let me get my calculator. Double check, make sure we're doing things here correctly. All right, there we go. And then are dividing it by 1,000 again, because this voltage is provided for us in units of joules per coulomb, which is the same as volts. Okay. So, you do the same thing here. What was this voltage? Was it 0.43, I think it was? If you forget, you can look back on that slide. But identify what the delta G is for this reaction. All right? Identify what the delta G is for this reaction by using our equation here. Jot that down for you here. Delta G equals negative NF E cell. Okay? The only kind of thing that's new here and something that we might not be comfortable with is our N, right? What value did you get for N in this scenario? Show your neighbor how you know what value we're supposed to have for N. It's 2, right? It's supposed to be 2. It's 2 because we see that lead has to